Hello, my name is Jin Yan. I will be presenting the paper Towards Understanding Man-In-The-MiddleAttacks on IEC 608705104 SCADA networks. First of all, let's see the acknowledgement of this paper. Okay, so here is the list of the authors, and this paper was originally presented at the Second International Symposium for ICS and SCADA Cybersecurity Research in 2014. If you are interested in this paper, you can use the link provided below to see the original paper. Okay, I would like to start with the overview of this presentation. There are 8 parts here. Motivation of this paper, overview of the paper, background, IEC 608705104 protocol packet, payload structure, anatomy of an attack, and then the most important part is these 2 experiments in this paper. And then finally, the conclusions of this paper. First, let's see the motivation of this paper. The key to successfully protecting systems is to understand the types of vulnerabilities and attacks which are possible. This paper allows readers to see exactly what the effect on a target ICS might be, where the cybersecurity issues are, and what measures may be needed to protect affected systems. The main intention is to develop a comprehensive strategy and set of tools to enable the detection of these sophisticated man-in-the-middle style attacks. The overview of the paper. This paper investigates cyber attacks on ICS, which rely on IEC 608705104 for telecontrol and communications. The main focus of the paper is on man-in-the-middle attacks, covering modification and injection of commands. It also details capture and replay attacks. An initial set of attacks are performed on a local software simulated laboratory. Final experiments and validation of a man-in-the-middle attack are performed in a comprehensive testbed environment in conjunction with an electricity distribution operator. Background. I would like to introduce some concepts which are important to this paper. For example, what is IEC 608705104? What is man-in-the-middle attack and the replay attack? Also, I will introduce some of the existing publications which are related to this paper. The first concept is IEC 608705104. IEC 60870 is a collection of open standards written by the IEC regarding the transmission of SCADA telemetry control and information. This was originally written for serial communications, but with the subsequent release of the 608705104 standard in 2000, it allowed for the same serial frames to be transmitted over TCP/IP. The 104 protocol is widely used in control communication for water, gas, and electricity. To the best knowledge of the authors, there's a lack of detailed publications. Attacking systems depend on the 104 protocol. Since the experiments in this paper investigated packet replay and man-in-the-middle attacks, I would like to introduce the concepts of these two attacks before we go into details of the experiments. A man-in-the-middle attack is where traffic is intercepted between two hosts and the data monitored or modified in transit without being detected by the victims. A replay attack is where valid data transmissions are captured and replayed by an attacker. Compare these two attacks. A replay attack is actually one of the lower-tier versions of a man-in-the-middle attack. A man-in-the-middle attack is more dangerous than a replay attack as it happens in real time and is harder to detect. I also want to introduce a little bit of the existing publications which are related to this paper. Much of the existing works are based on Modbus and the DMP3 protocols. In comparison to 104 protocol, is also vulnerable to many of the same kinds of attacks. A key vulnerability for most systems is the lack of authentication or validation mechanisms for data communicated via 104, and similar protocols such as DMP3. Robinson covers possible attack vectors such as lack of protocol security in Modbus and DMP3. Morris and Gao investigates attacks such as response and measurement injection, and command injection using the Modbus protocol. Peter Camperset brings to light issues which ICS system administrators might overlook, and seminally discusses ways in which it's possible to perform stealth and semi-stealth man-in-the-middle attacks using ARP spoofing. Timorin explains how to detect IEC 60870-510 devices on the network, and also releases Python scripts which can identify and return the common addresses of a 104 device. So there are the existing works which are related to this paper. So these above are the experiments. So these experiments presented in this paper are to some extent based on these existing works above. Before discussing the experiments, it's first necessary to highlight the relevant features of the 104 protocol, which are most significant to the work. Figure 1 shows the structure of a 104 packet payload, which is referred to as the Application Protocol Data Unit, APDU. The APDU consists of two parts: the Application Protocol Control Information, APCI, and Application Service Data Unit, ASDU. The APCI is used as a communication, start and stop mechanism for the ASDU. The APCI contains a start character 68, as you can see here, a length field, and a control field. The ASDU contains the application data, such as the device common address and the system readings contained in information objects. Therefore, this is the location of the most critical data for physical system, and this is where the focus will be for the attacks carried out in these experiments that follow. Okay, next. Anatomy of an attack. The paper proposes that attacks can be classified into different levels based on the knowledge required of an attack. Table 1 shows the 4 levels of attacks. The experiments that this paper presented are in such a way that an incremental level of knowledge and technical sophistication is required at each stage in order to successfully execute each attack. We will go through these experiments later. Okay. And then the motivation is to both understand the attacks and classify the kind of attackers that would be able to execute such attacks. An attack will follow 3 steps, as you can see from the figure 2 here. The first step is detection, where targets are identified. And the second step is capture, where data is collected in preparation for an attack. And the last step is attack. Now, we will look into more details of each step. The first step is detection. There are 2 ways to detect 104 devices attached to a TCP/IP network: passive and active. Passive detection is where no action is taken. The interface will accept all packets on the wire. Packets can be monitored for 104 traffic with tools such as Wireshark and TCP dump. 104 traffic has been identified. It can be locked for future use, such as replay attacks, or passed to identify attack targets to be used in a future attack. Active detection is where packets are sent out from the machine to try to invoke a response from a 104 device. One example is Timorin, as I introduced in the existing works. He has written a Python script which probes a list of IP addresses and returns the common address of a 104 device if it exists. The passive method may be used by a novice hacker who is not sure what is going on in the system, probably level 2 in the attacks level table I just showed to you before. And the active mode will most likely be used in conjunction with the passive technique to confirm the existence of the 104 device and to obtain detailed information. It will be used right up to level 4 in the attack level table I showed to you before. The next step is capture. It is possible to capture data by monitoring and performing a man-in-the-middle attack. Typically, data can be captured using a span port, which is used on a network switch to send a copy of all packets on the network to a specific port. If an attacker is able to gain access to a machine which is connected to a span port, they will be able to capture all the traffic passing through. Another way is to get in between the 2 or more targets and capture data. First is to use ARP spoofing. ARP spoofing takes advantage of the fact that ARP, like 104, does not support verification and authentication. An attacker can send spoofed ARP messages, which associate the attacking machine's MAC addresses with the target's IP address. So every packet which is addressed to the targets will arrive at attacking machines. Now, the attackers can view and edit all packets being sent between the targets. Alternatives to ARP spoofing: we can use DNS poisoning and CAM table overflow attack. It can overflow the memory of the switch and turn it into a basic network repeater. The final step is attack. Since this paper focuses on man-in-the-middle attacks, this session is limited to directly related attacks, such as replay and injection. First, replay attack. The data may be replayed with or without any modifications. If the data is replayed without modification, in an ICS environment, it might mean duplicate readings being sent to the monitoring station. Such attacks would be performed by an inexperienced attacker after level 2 in the level table. Okay, and this will be discussed in more detail later in experiment 1 replay attack. The next one is injection attacks, is where the values are modified before they reach their target. A man-in-the-middle attack would be performed at level 2 or above. This will be discussed in more detail later in experiment 2 man-in-the-middle attack. First, let's see experiment 1 replay attack. In this experiment, a replay attack is performed with packets captured from software based on emulators. The goal of the attack is to capture 104 packets and replay them against the targets. This is a relatively simple form of attack, hence, according to the attack level table 1 I mentioned before, this would be level 2 or below. So you can see here, figure 4 details the test network, which consists of a master and slave 104 device, Snowed IDS, Splunk log analyzer, and a Kali Linux attack platform. QTester3 is used to emulate the master 104 device. This emulator makes it possible to pull and view data from the substation system. The substation slave device is simulated using the WinPP1044 packet simulator. It is used to generate measurements and reply to interrogation comments from the master. Figure 5 is a screenshot of QTester running. The menu bar at the top allows us to specify the details of the slave to monitor. The top menu also provides the feature to send command instructions to the slave. And then the left-hand main pane outputs the log message. The pane on the right details the data received from the slave. Figure 6 is a screenshot of WinPP1004 running as the 104 slave, which is connected to QTest master. The main pane of WinPP details 104 packets sent and received by the emulator. The top table displays statistics of the connection. The window at the top right allows us to specify the 104 packet to be transmitted to the master. From here, it is possible to set the frequency of the packets to be sent. The type can be selected. In this case, it is type ID 31 and double point information with timestamps. The timestamp can be specified in the lower half of the dialog. The cost of transmission can also be specified. In this case, it's 0, as you can see here. Okay, and finally, the information status and the qualifiers can also be set. Connected to the spam port of the switch is Snort. Snort is running customer rules to detect anomalous 104 traffic. Splunk is used to display alerts from a Snort, and monitor the network for anomalies. Figure 7 shows one-over traffic between the safe and the master. The top left bar, as you can see here, the bar chart shows a count of the different costs of transmission detected. And then the pie chart on the right details the total 104 types. And the line graph at the bottom shows the number of types detected over time. Packets used for the reply attack are captured from the spam port of the switch. After capturing a packet dump of significant durations, Wireshark is used to remove non-104 packets from the capture. This leaves just the packets from the target machines, which consists of TCP/IP handshake initialization 104 packets. The Kelly attack platform is where the packets are replayed from, although the replayed packets are not accepted at the application layer due to the packets being dropped by the kernel's TCP/IP stack. Figure 8 shows the Wireshark detecting the replay by highlighting it with the retransmission flag. From this experiment, we know that it should be possible to detect the malicious activity investigated above using existing SNOT rules and the statistical analysis of network traffic and logs. Furthermore, since the packets replayed will not be accepted at the application level of most systems, this level of attack should not directly affect the operation of the ICS. With further efforts, it will be possible to replay the captured packets so that they are not dropped by the kernel and are accepted at the application layer. Now, let's see experiment 2. This experiment conducted within a realistic electricity distribution SCADA environment established by the Precise FP7 project. So what is Precise? Precise aims to investigate cyber threats and develop tools and methods that detect live breaches of cybersecurity and provide early warning alarms. The development and construction of the comprehensive testbed environment has been undertaken by Lindstrom. The Linz testbed site primarily comprises a SCADA process network, substation process network, and an office domain network. The environment is presented in Figure 9, as you can see here. The substation and SCADA server network elements highlighted in Box A and Box B are the focus of the following experiment. These two domains in the testbed contain RTU devices and SCADA control services in a configuration that mirrors as close to a real operational environment as possible. The 104 protocol is used for monitoring and control of this ICS. This experiment monitors for specific 104 traffic in order to carry out a targeted attack against the core ICS control communications. Once specific SCADA packets are found, they are modified and forwarded to the SCADA server, where they will be accepted as if they originated from this RTU device. There are two implementations of the Man-In-The-MiddleAttack presented in this paper. The first is the laboratory simulated environment, and the second is the real testbed environment. Let's look at the implementation in the laboratory simulated environment first. The implementation of this attack is to alter the COT field. In this experiment, the emulated slave RTU device has been configured to transmit a spontaneous 104 packet of type ID 30. When exiting this attack, the attack plugin monitors for 104 packets with a type ID of 30 coming from the slave to the master. When an appropriate packet is detected, the original packet will be dropped by the man in the middle and a new packet crafted with a modified COT. The COT value is used to route the ASDU to the correct program or task for processing. So here, figure 10 shows a packet capture of an unmodified packet being sent from the slave to the master. As you can see, the COT value is still set to 3. Then figure 11 shows a packet capture of the packet after it has been processed by the plugin. Here you can see the COT field is changed to 42, as you can see here, which is unused and causes a snap to trigger an alert. And then you can see the figure 12 here. This rule checks to make sure that each packet has the correct course of transmission based on the specification of the 104 protocol. Now let's look at the implementation in a real testbed environment. The second implementation is in the links tested site, where a specific SCADA operation is targeted. It is intercept and modified information contained within the ASDU. Using the precise electricity distribution testbed, we have a scenario where the input-output port of an RTU is being turned on and off at regular intervals for monitoring and testing purposes. The objective of this attack is therefore to intercept the on value so that an off value is received by the SCADA server, thus hiding the real status of the physical system from the engineer in the operations control center. 104 stores this data within the information element. Each ASDU may have 0 or more information objects depending on the type of data being transmitted. So figure 9 details the test network used. The network PN CSADA server. Section B is where the control and attack machines are located. So you can see here. The SCADA server is the main control unit and is the target for this attack. Kali is used to simulate a compromised machine and is used to perform the attack. And it's also located here, as you can see, the box. Oops, go back. Okay, and then so they transmit the packets containing the switch on-off values. The first stage of the attack is to perform an ARP pointing against the targets. This will allow the attacker to become a man in the middle and monitor the communications. The next stage is to monitor for ASDUs, which contain an information element with the SPI field set to on. If the value is already set to off, then it will be allowed to pass through. Once an ASDU is positively matched, the packet will be dropped and a new packet sent, with the SPI value set to off. The outcome of this is that the control station will only ever see packets with the SPI value 0 off. And so here, figure 13 shows the power circuit and displays any alarms to the operators. For these two implementations, we know that the first implementation in the lab environment was the first step towards proving the function of the attack plugin. Such scenarios are most likely to arise if the attacker does not have a good level of domain knowledge about the ICS. In contrast, the second implementation in a testbed environment requires a large amount of domain knowledge. This attack could only be achieved by someone with abilities of level 3 and above. Finally, we would highlight that although in this experiment we have only modified the COT and SPI fields, the plug-in tools developed here allows change to any field or the ability to substitute the packet with any other packet without limitation. In conclusion, this paper has examined a series of cyber attacks against SCADA systems using the IEC 60870-5104 protocol. These range from some basic replay-style attacks to a more sophisticated man-in-the-middle attack. One of the main purposes of this work was to enhance the existing literature in relation to SCADA-based attacks, particularly man-in-the-middle attacks, which are not as well explored as DOS, packet injection, device discovery, and so on. Over the course of these experiments, it has been shown how attackers with various abilities and domain knowledge can compromise the integrity of the SCADA communications with an ICS. Finally, the main intention following from this work is to develop a comprehensive strategy and set of tools to enable the detection of sophisticated man-in-the-middle style attacks. That's all of this presentation. Thank you very much.